Hello everyone, it's Mr. Geringer again, and this is the mathematics, this is chapter 7.3, Kruskal's algorithm. So we've been talking about taking full graphs, graphs that maybe have circuits or, well, ones that don't qualify as trees, and we've been pulling spanning trees from them. They're the subgraphs. We've been trying to create these spanning trees because the spanning trees are what we're actually working for. We're trying to get these networks, and that's what we're going. So Kruskal's algorithm is a way of finding the minimum spanning tree. It is, if you remember the cheapest link algorithm, it's almost exactly like that. The cheapest link, remember, that's from the Hamilton circuit unit, where all you do is you focus on the smallest or cheapest links. So second bullet, we choose the cheapest link that doesn't close the circuit, and then this particular algorithm will trace the minimum spanning tree. And it is very efficient because you're only picking those things that you need, and it is optimal because it will always pick, or you will always pick the smallest possible numbers. So here are these are things that you should know about the algorithm. It gives optimal and is efficient, and remember, the minimum spanning tree is the optimal solution. So take a look at this example. We have, which probably some type of phone line. We're connecting all of these cities, El Dorado, Cayman, Boaz, so forth and so on. So we've modeled this problem in figure B. We've assigned, which could be maybe distances as the weights of the links. And so now we need to use Kruskal's algorithm in order to find the minimal spanning tree. Let's take a second to discuss this, though, before we do. You guys realize that the idea of a network, once your PC is connected into the network, it can pretty much reach every other node on the network. As long as the address is correct, then you can reach every node. So all you need is one line coming from one node to another node, and you can reach all the other nodes. So when we're trying to build these trees, if you select all the cheapest links, then eventually you get to a point where you have chosen all the ones that connect the nodes. So that's what I'd like for you to do. If you pause this video and take a second to see if you can trace the minimal spanning tree by using Kruskal's algorithm, only choose the cheapest links that do not close a circuit. So for figure A, we look at all the numbers here and we find that FG is the cheapest. So we go ahead and select that one. And then we're looking for, the next one was 45, which I have here. Let's see, I'm going to trace A, but you can see it in B. So 45, then after we choose 45, we pick 49. Now notice we are not connecting them yet. Remember, in the cheapest link, we did not care if they connected. We are only picking the cheapest link. The reality is as we continue to pick them, they will eventually connect, but they don't have to connect at the beginning. So we're just choosing them. All right. So the next one after the 49 is the 51. So that's the figure that we have down here. Okay, the numbers are $1 million to lay this pipe. Anyway, so we have what's in figure B now. So we're not done. Whoops. This is just going through what I just did. So step 2, of course, is the next one, 45 million. Step 3, the AD, the 49 million. And then finally the 51. After that comes the, well, this graphic's kind of funny. It eliminated this one because it was 51, and of course that would have completed the circuit. We know it's not going to be this one because that would also complete a circuit. So those two are completely out of there. So the next cheapest one in our graphic here is 55. And when we do 55, that eliminates 64 because that would complete a circuit. When we do 55, it also eliminates 56 because that's a circuit. And so now we only have two choices, right? We can go C to E or F to E. We want the cheapest link, so that makes this the cheapest link. So this is more steps that just walk you through what we did. 53 was next. And when we chose 53, it eliminated a few things. So the next one that we chose, well, it was the 59. Yeah, that's what this step says. I went too fast, but that's okay. And at this point, we're finished. If we look at it, we are looking at a tree. It's a minimum spanning tree. 6 links is what we needed because we have 7 vertices. And now we can add up all the numbers associated with it and find out the total cost of the network is $299 million. And we know that this is the minimal spanning tree. We did it quickly, so it's efficient, and we found the minimal spanning tree, which is optimal. So here's a fun one. We're going to go ahead and go through this, go over this one in class. But what I'd like for you to do is go ahead and put this on hold and put the video on hold and see if you can pick, using Kruskal's algorithm, pick the cheapest link here and find the minimal spanning tree. So go ahead and try. I'll be right here. Go ahead. So here's another fun example. If you look at this and you could be able to identify, yeah, you can identify all of the cheap ones. So go ahead and attempt this and we'll check our answers in class. And I do believe that finishes, yes it does, it finishes the chapter.